Check. 1, 2, 2, 1, 2, 2, 1. Oops. 2, 2, 1. Check. 1, 2. Check, 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 check. 1, 2. 2, 1. Check. 1, 2. Everybody can hear me. Check. 1, 2. 2, 1. Check. 1, 2. 2, 1. Testing. 1, 2, 3. Check. So here we are. Blah, blah, blah. Blah, blah, blah. A little bit less. Check, check. 1, 2, 2, 1. Test. 1, 2, 3. Check. 1, 2. Check. 1, 2, 1, 2, 3. Checking. 1, 2, 2, 1. Hello, hello. Check. 1, 2, 2, 1. Check. Okay. Check 1 2 2 1. Check 1 2 2 1, and then I have the lavs. But this is my wireless set.
Yeah. Oh, that's fine.
Yeah. Okay.
I have the new wireless set.
Do do do.
Check, check. Check. Check 1, 2. Check 1, 2. A lot of feedback. Check 1, 2. Check, check. Check, 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 check. Check 1, 2. 3, 4. Check. Starting to sound better. It's off.
Check. This is lot one. This is lot one. Check 1, 2. Check 1, 2. Check 1, 2. Check 1, 2. 2, 4, 1. 2, 4, 1. Check 1, 2. Thank you for visiting Denver, the Mile High City. With over 300 days of clear blue sunny skies, Denver is the place. From our magnificent selection of restaurants, museums, and other outstanding cultural facilities to the magnificent beauty of the Front Range. Check 1, check 2, check 1, check 2, check 1, check 2. Testing 1, 2, 3. Test 1, 2, 3. Check 1, 2, 2, 1. Check 1, 2, 3. Check 1. Check 2. Check 1, 2, 3. 1, 2, 1, 2. 1, 2, 1, 2. Check 1. Check 1, 2. 2, 1. 2, 1. Check 1, 2. Check 1, 2. Check 1, 2. Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Thank you for visiting Denver, the Mile High City, with over 300 days of clear blue sunny skies. You can hit mute on that.
What's it?
There's a little microphone right here. That'll tell you that should be unmuted.
Check 1, 2. Check 1, 2. Check 1, 2. 2, 1. Check 1, 2. Sounds pretty good, actually. Okay.
Check 1, 2, 2.
Good. Nice to see you,
Check
John.
1, 2. Hey, how's it going?
Pretty good. Pretty
So
good.
parking was a little rough today, was it?
Yeah, I had to park like 4 blocks away.
Oh man, I'm so sorry. The last
And
minute
it was like I parallel parked with like this much space on both sides of my car.
Right. So you had a little bit of both going on. Well, you know, this Rhino, last night I came down here and I came through downtown, and oh my gosh, I got so lost. I lived my whole life in lower downtown, and I could not find 36th Street to save my bucket. It was so funny.
Yeah.
And setup was a breeze. It took me 2 hours to get everything tested out and signed up, and I was all worried. I was down here at 6 o'clock this morning just to double check and make sure.
I used to come to this neighborhood a lot. There's a place here. It used to be called the Expo Center. It's like a block on 37th and Walnut.
Mm-hmm.
It's a big event space, like for
Right?
and so it's been fun watching this whole place
Yeah.
blow up.
Hey, are you busy tomorrow morning? You got a gig?
I don't think so.
Well, I got a deal for you. I rented a projector to the group that's coming in right after this one.
Okay.
So all you need to do is come in and hook up their computer in the morning and be on call. Not run, you don't have, you can go home. It's not going to do anything. It's a projector.
Okay.
And if they have issue, you'll be there at lunch to fix it. I'm going to run it into these screens as well as a projector.
Okay.
So if the projector bulb blows out, there'll be a spare here.
Okay. Okay. Let me just confirm.
Check 1.
Yes.
You want me to check this handheld as well?
Might as well.
Check one, check. Check, check. Oh yeah, perfect. Check, check. Yeah, for Q&A. Cool. Excellent. Well, that sounds good there. Yeah, no worries.
Check, check, 1, 2, 2, 1. Check, 1, 2, 2, 1. Check, 1, 2. It's been streaming for an hour, so I'm not hearing it here. Check, 1, 2, 2, 1. Check, 1, 2. Check, check, 1, 2, 2, 1. Check, 1, 2, 2, 1. Check, 1, 2, 2, 1. I'm not hearing it over here. Test, 1, 2, 3. Test, 1, 2, 3. Check, 1, 2, 3. Check, 1, 2. Check, 1, 2. Check, 1, 2. As soon as it switches. Yeah, I can hear it. Check, 1, 2.
Check 1, 2. Check 1, 2. Am I good to go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's a little echo. There's a little echo.
Yeah, it's
It's a bit too high or a bit too low.
it was a bit too low.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Are we good? Sorry? Count forward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's still an echo. Stay here. Okay. Should I try one more time?
No, it's good.
We're good to go.
When you stand in front of the speaker, then you sometimes get interference.
Okay, got it.
Check 1, 2, 3, 1, 2. We're going to be starting in about 5 minutes. 5 minutes.
Good morning, everybody, and thank you for coming. This event is also broadcasted, so if you are listening from somewhere else, welcome. We're actually monitoring the questions, so if you have questions, please feel free to interrupt at any time. I thank everybody for coming. Special thanks to Laurie Blon, who started this event, also David Steinbrook, who is here. Maybe you come, people see you. And hi, and Uri Kirsten, and so they set the program. I'm only going to give you kind of the introduction. Other people will give you more technical stuff. We have assembled actually, I think, the key players in this space, and please feel free to ask them questions. We set some time for the talk, and I'm going to monitor it, but please ask questions while the talk is there. There will be lunch at 12:30. I want to basically start this event by kind of trying to explain, I've been in this space for about 4 years, the relationship between formal method and DeFi. I see actually that most of you are formal method geeks. Are there somebody here who is not from formal method? I think, well, you can count or no? Is there, who here is not from formal method? Okay, that's great. Okay, Jeremy, we have Jeremy. So formal method is a mature field in computer science. It's basically the idea is you have a program and you want to formally verify that it does what it's supposed to do, and actually alternatively you want to find some behavior of your code which are bugs, which violate the specification. Formal method has been around for a long time, actually going back to Turing. In his original paper on computers, he actually described the idea of formal methods, but a lot of people, and I pointed out some of them here, but many people actually contributed significant techniques in this field. I have this quote here by Dijkstra saying that program testing can only show the presence of error. In my opinion, it's actually an unfortunate quote, because in fact we want to have testing, and actually one of the beautiful things of formal method which has been shown in the area of hardware is that actually formal method can find bugs in your code. And formal method is used, for example, in hardware to find bugs before the code is deployed. And we see the idea that actually smart contract and DeFi, they are interesting because they are somewhat to the hardware verification. So why do we actually want to use formal method for DeFi? We want to use formal method for everything. But in some sense, formal method, DeFi is the killer application of formal method, because it's a unique domain where actually you don't need to convince people that you need formal methods. Because one of the things that happen is that in the area of DeFi, code is low. The code is immutable and the code is low. So if you have a wrong code, it's almost like hardware. You have the wrong law, and it's hard to prevent that. And also, the idea is in formal methods, in the DeFi, the idea is that the code carries a lot of value. So if you have a small mistake in your code, it can actually cause you to lose all your assets. And we are seeing examples like this. And another thing which is interesting, we know that formal method is a method which is hard to apply to large programs, but in the area of DeFi, the code is either small or modular. So the idea is there is more potential to apply these techniques. But still, the code, even though it's small, it's tricky. There are many behaviors, so it's hard for people to find this kind of bugs. And maybe the most interesting thing about DeFi is that unlike avionics software and other cases where people have applied formal method, it's the case that people want to constantly innovate. They want to build new and new stuff. So that's why actually you need this kind of formal methods. And I pointed out two quotes by two industry leaders who are actually using or planning to use formal methods. Actually, this is kind of a slide that we came lately. One of the interesting things of this domain is how do you use formal methods? And formal method, even though it has been in academia for a long time, there is not a clear usage methodology. How do you use formal method? And this is my attempt to try to explain how you use formal method. So in the top, oops, I'm going the wrong way. In the top, you have the DAP. You have the DAP, and this is like a normal development cycle. You start by the design, you come with a white paper, then you implement it in Solidity or in another language, and then you have the code, and eventually it's deployed. So this is the normal development cycle, but on the bottom, in the green, you see how formal method fits into the play. So formal method can start as early as in the design. You are designing your code, and you want to have some kind of requirement. You want to know what are the requirements for your code to behave correctly. From there, you come with a formal specification where you use CVL, you use temporal logic, you use kind of way to formally specify your code. And then you do kind of two things. You can check that your code satisfies the specification, which you use formal method, or you can check that the specification itself is okay. And basically, this is what you do to check the code. And from there, you are producing something like a verification report. It's some kind of a document, show what you verified, what are the properties that fail. And on top of it comes what is used in the DeFi, which is called manual audit. So there is a human, and the human can check the code, can check the white paper, it can check, he or she can check the spec, and eventually the human will produce a report, and this report is actually deployed when the code is executed. So this is the way that all of these fit together. And we, as technology provider, we provide techniques for using these things. So this is my introduction. I want to basically now introduce the great speakers. I think not all of them are here, but most of them are here. So maybe you can come to the front and say a few words. I see Will here. Yeah, no, but yeah. No, yeah, I just want to first, basically we have the introduction for all the speakers, and after that Will will speak, I will introduce him. Yeah, welcome, Will.
Thanks so much. So I'm Will.
Yeah, good idea.
There we go. Excellent. Fantastic. So I am Will. I'm a co-founder of Syndicate. We've been using Certora for multiple years at this point. We essentially run a platform for investment DAOs. So we have a modular architecture where you can track deposits, member management, distributions, and essentially fund flows through investments. We have hundreds of thousands of users and have been using formal verification and other methods like testing, fuzzing, and auditing to secure many millions of dollars flowing through the protocol.
Thank you very much, Will. So we have the other speakers. Please come. Never.
I'm on my way.
Okay. Can you read this?
Sure. Hey everyone, I'm Everett. I know most of you here. I run time verification. We build formal method software based on semantics first approach. And so today
Yeah, so I'm Julian. I'm the head of formal verification at Nethermind, and I'm going to talk today a little bit about our Horus tool for verifying startnet smart contracts. So we work a lot in the like ZKVM sort of area, basically, and you'll be hearing a bit about that. I'm giving today a more technical talk, and then tomorrow at the startnet event, I'll be giving a more practical talk showing actually how to use the thing. So, although misleadingly, both talks have the same name. That was probably not the best move, but anyways. So, there you go.
Hi everyone, my name is Ishal Dilek. I am a co-founder of Veridice, and I'm going to be today talking about our security as a service platform that we've been building. And since everyone else was advertising other talks to come, I'm also going to advertise that we do have a talk in the main EAT Denver event on March 4th, so that's going to be in 2 days. I'm not going to be here, but John is going to be talking about our the tools that we've been building for certifying your ZK circuits.
Awesome.
Thank you. Yeah. So my name is Wolfgang Reiskamp, and I'm from Aptos. So Aptos is the new layer 1 blockchain, which came out of the Beat project at Meta, or Libra. I think it's better known as Libra. So I'm the lead of the move language platform at Aptos, and we have worked on formal verification for Move for quite a while at Meta, for I think nearly 3.5 years or so. And I'm happy to report about this today. Aptos itself has an Aptos house here on Saturday. So if you want to know more about the technology, you're very welcome to drop in. Though I'm actually not knowing whether there's a registration limit or anything. I have no idea. Thanks.
Thank you very much, everybody. Yes. So with me, I introduce Will Fetter, our first speaker. So actually, I've known Will now for about 3.5 years. And, oh, sorry. Should be here? Oh, it doesn't work?
So,
Okay. So I've known Will for 3.5 years. Actually, sort of starting to work. I think he's one of the earliest guy writing formal specs. Actually finding so many problems, mainly with our tool. We met in Palo Alto, maybe. He was finished his degree in Stanford. And later he joined Yahoo. I think they are kind of formal methods, and we know people from this field. It's very hard to use. And actually they've been using it in a better way than we. And let's hear what they have. I think he wants to have questions during the talk.
Yep. Absolutely, yeah. So we've been huge fans of Certora. We use them ever since the documentation was a single Google Doc, and it's been incredible seeing the tool improve and develop over time. So first, I want to get a sense of everyone's experience levels in the room. So quickly, just raise your hand if you've written. What about tests for Solidity code?
Check 1, 2.
Cool, cool. Fuzz tests? Nice. Same number of tests and fuzz tests, good. Undergone an audit for Solidity code. Okay. And written formal verification specs for Solidity code. Okay. A lot more people into formal verification than auditing here. Very interesting. So I'm going to give a quick overview of the security landscape and how we use it at Syndicate. Oh, it's notes. Yeah, yeah. So a quick overview of the security landscape and how we use it at Syndicate, and then a little bit about why formal verification matters for us, and then how it improves our development velocity. So this is just a quick overview. So the first part of the security landscape we use at Syndicate, of course, is testing. Test a specific set of inputs and outputs. We use Foundry for that. We love writing our tests in Solidity and our code in Solidity. It makes it very easy to test compared to Truffle and Hardhat. If anyone is on Truffle and Hardhat right now and you've been considering Foundry, writing your tests in Solidity will change your life, I promise you. It is definitely worth making the switch. The second piece of the security stack we use at Syndicate is fuzzing. So instead of testing a specific set of inputs and outputs that we specify, we test the randomly generated range of inputs and outputs. And the fuzzer has a bit of intelligence to it, so it will automatically test zero values, max values, min values, things along those lines. The third piece of the stack we use is auditing. Of course, as Millie talked about, line-by-line review of the code, fantastic for spotting issues with interactions between your contract and other contracts. So if you're working on contracts that leverage oracles or leverage debt markets or leverage essentially other contracts in the ecosystem, auditing is really good for that and for spotting issues with external contracts. Formal verification, of course, you're testing contract invariance. So you specify, instead of specifying inputs and outputs, you specify reachable and unreachable states that you want the contract to have. And then the formal verification tooling, in our case Certora, tests all possible paths to get there. What we love about it is that it's the only part of the stack that essentially flips the mindset about testing. So everything else, it's very much you have to be looking for certain things. You have to essentially state, okay, here's what I expect to go right and go wrong, and I'm going to look for that. And that testing, fuzzing, and auditing is all in that mindset of looking for correct cases and incorrect cases. The thing I love about formal verification is that you don't think that way in terms of what are the specific inputs and outputs I want to be correct or incorrect, but instead it flips your thinking, and you have to think, okay, what are the contract states that I want to exist or not exist? Instead of thinking about the input states and how you reach the output, you start from the output and you move backwards. And that is fantastic because that gives us a type of coverage that nothing else in our security suite gives us. Formal verification, it's fantastic because it tests all paths, not just the paths you think to test. That has caught issues for us in the past, and that is easily the single biggest thing that pays dividends for using it. And it's also excellent for catching issues internal to your contracts. So that way, when you go to an audit, the audit can look at the formal verification specs, know that the contract itself operates as expected, and can spend a lot of time thinking about ecosystem interactions. So in general, it both makes your audit faster and therefore cheaper, and also lets them spend time on things that are much more differentiated than things where manual review can play a larger role. In the development cycle at Syndicate, formal verification lets us launch faster. So it gives us the confidence we need to do guarded launches. Because if we can guarantee that a contract's internals are correct, then the main risk is interactions with the rest of the ecosystem. And with a guarded launch, we can get to the point where we're comfortable that, for example, like there's not enough capital that we don't use oracles, but like in theory that there's not enough capital that flowing through it that like oracle attacks could be a problem. You can get to the guarded launch before the threshold you're comfortable with, the threshold you'd be comfortable with if there were any issues, and the guarded launches we are able to do with formal verification alone and then audit after. Formal verification also gives us a lot of confidence when touching any part of our code base. So we have a modular architecture at Syndicate. Essentially, we have many, many contracts specifying different parts of the behavior. So for example, we have a contract dedicated just to tracking deposits, or a contract dedicated just to handling the renderers for an NFT, what metadata it exposes. And because formal verification is running in our CI/CD pipeline on every single commit, we can make a change to one contract, and we can know that everywhere else it's used, that the overall system invariants remain the same. So that allows us to use it for things like permission checks, deposit and withdrawal checks, token management checks, and transfer and ownership checks. And all of that ladders up to confidence when making changes because even though our modular architecture is highly interlocking, formal verification lets us verify individual modules and then also the interaction between modules in our contracts. I also want to talk a little bit about how to set your team up for success. So there's two options that many companies pursue. One is to dedicate engineers specifically to writing specs. I'm curious, for those of you writing formal verification specs in your company, how many of you have an engineer dedicated to doing that task? Cool. And then how many of you have every engineer write their own specs? Cool. Roughly 50-50. Very interesting. So we did the first option at Syndicate for a long time, where we dedicated a single engineer to writing specs. That was a great approach because it gives us a second set of eyes on everything, because we've separated implementation from formal verification. So if someone, for example, has wrong assumptions in their implementation, the person writing the formal verification specs provides a second check to that. But the downside of that, of course, is that you then, the rest of the team does not get the same experience. So we're actually moving to the second option right now, where everyone will write their own specs throughout the team, and then other people will check their code and their specs and PR reviews. And that will allow us to have better knowledge, because that way we can all jump in on debugging, for example, specs or contracts when needed. And it also lets us bootstrap this understanding in a way where people can more easily pair on it. So that's a little bit about how we've used formal verification in practice at Syndicate. In summary, it speeds up our development velocity dramatically. It lets us do guarded launches. It lets us essentially focus on the internal correctness of our contracts. So then we only need to worry about, for audits, how we interact with the rest of the ecosystem and external contracts. And it gives us confidence when touching any part of our code base, because we know that all of the invariants will hold upon every commit. So we have approximately 10 minutes to chat about essentially either any questions about anything I talked about, or what you've seen using formal verification in practice in your companies.
Questions?
So I'm really curious. Oh yeah.
You mentioned several techniques. I'm just wondering, like, which ones your developers tend to prefer for their quality assurance in general. I mean, you clearly stated truffle is not the way to go. You like to switch to Foundry for sure, but you've got like several different techniques at varying level of firepower. How much time are you spending on each one? Like, is it like 50% writing property tests, 50% Certora? Well, not another 50% somewhere else, but just kind of give a rough idea of that.
Yeah. So we'll always sequence it where we'll start with the tests first. I mean, those are the most straightforward. Those are the ones that get closest to the implementation logic. So I'll write the tests first, and that takes up I'd say like the bulk of the testing time. And then afterwards, one thing I love about Foundry is that fuzz tests are really simple to write. So for fuzz tests in Foundry, for everyone here, essentially you instead of specifying your inputs inside the test itself, you just specify in the function signature, okay, I'm going to have a uint256, and I'm going to have, for example, an address. And then the fuzzer will generate everything from there. So you can stick very close to your implementation tests with your fuzz tests, which is nice. They don't take that long to write. And then on the auditing side, internally, we'll do a line-by-line review of every single code by every protocol team member before it goes to production. So that's time-consuming, but outside of the scope of writing code for a given feature. And then formal verification, I'd say, is probably equal in terms of the time we spend on testing and fuzz testing. A little bit faster because we already bootstrapped a lot of the logic and have figured out the implementation between the code and the tests. But we save it for last, and then we essentially flip our thinking when we write it, and we say, okay, now it's about contract states, now it's about reachability. And saving it for last, oftentimes, we'll then go back and we'll clean up our code or we'll clean up our tests based on what we learned. So that's one thing also is like initially, when we first got started with formal verification, we thought of it as basically just a security tool. Like, oh, okay, it gives us a higher level of assurance. But then what we've seen in practice is that it also leads to much cleaner code, because when we start reasoning about the contract states, we often find more effective ways to get there in the implementation. So there's times where we'll then go back after writing the spec and rewrite the implementation and the tests in response to the way we've thought about it. So it's something that in the life cycle improves the overall code, and that's also why we're transitioning to engineers writing their own specs, because then they can go back and change the implementation based on what they've seen.
More
questions? Cool.
Do you code review your specs as well as your code?
We do. I mean, just being very upfront, the implementation gets the most scrutiny, and then the tests and formal verification. So it does go through code review. It gets somewhat less scrutiny than the implementation logic itself. But one thing we do, it's actually really nice, is that we very, very rigorously comment our specs with the desired behavior that we want. And then we keep the specs very, very, each spec we keep very concrete and very tightly scoped. So oftentimes, if I'm trying to, for example, get a sense of a contract that I might not have looked at before, I'll actually I'll first look at the implementation very quickly, but then I'll go to the spec next, because then I can know, okay, great, here's in general, like, it basically at a certain point specs out essentially like the end state of the flow, and then I can work backwards the tests and see the starting point of the flow. So we do put them through code review, and I'd say we treat them as documentation essentially. And then when auditors come in, they also bootstrap on the specs as documentation as well. So the implementation tests are helpful, but like, whenever I'm reading tests, I think to myself, like, okay, well, we're only thinking about what we're remembering to check. What are we forgetting to check? And then going to the spec file, having that case covered, and then also thinking in terms of like, okay, what are the overall states? Lets me then go back, and lets our auditors go back too.
And just to follow up, have you thought about moving some of that natural language specification earlier in the development process, or do you think that wouldn't be valuable?
So for us, because our modular architecture, each contract has a very small scope. Like, it will only handle ERC20 based deposits, or it will only handle ETH deposits, or it will only do checks of like, can someone transfer this token or NFT? Because our modular architecture is very tightly scoped, we don't write the specs first, because oftentimes like a single contract for us is like 3 or 4 function signatures. When we do novel architecture, it's very helpful in that way. But at this point, we basically wrote a V1 protocol, and Certora very politely told us that it needed improvement. And then we wrote a V2 protocol, which was dramatically simpler and a dramatically better architecture. And like, when we were doing the V2 protocol, we did think about like, okay, what are the overall states we want to reach? But for individual features that we add, typically not. Typically, the function signatures are self-documenting there.
Makes sense. Thanks.
Yeah.
More questions?
Test. Hello?
Just talk.
Hello?
Yep, you're good.
Yeah, what's your development cycle like? How long does it take? And maybe like how many, I guess a good thing to ask is how many audits have you gotten? Just
Yeah.
to, like, yeah.
Yeah.
How quickly are you developing code, and how many engineers do you have?
Yeah. So essentially, we have a total of 5 engineers touching the protocol in various ways. Some are dedicated exclusively to the protocol. Some do other work alongside the protocol, like backend. For novel architecture, like our modular architecture for 721M and 20M, that tends to take about 1 to 2 months, and it tends to be built by usually around 2 people. I think that many great protocols are often built by like 1 to 3 people. So when it's novel architecture, we tend to keep it very small, and we also run the protocol team with no deadlines. We intentionally run it ahead of all of the other work that we have, so the protocol team can really focus on rigor and correctness and not need to try to rush a feature out the door. And then individual modules for a modular architecture, that is, if it's a custom one-off module, like we're using it to satisfy a particular customer use case, that's typically 1 to 2 weeks, depending on complexity. 1 week is pretty much the minimum for getting through the full cycle of implementation logic, implementation tests, fuzz tests, and formal verification. 2 weeks if it's a heavier scope or not a one-off contract. 3 weeks if it's like something that's very far from what we've done before. And then we basically do audits after major architecture rewrites. So we did 2 audits for our V1 protocol and then 1 audit for our V2 protocol. And that's alongside Certora's formal verification specs as well. We want to do audits every 6 months. In the bull market, that was very hard because you need code freezes 3 to 6 months out. So in the bull market, by the way, like formal verification is what let us launch quickly because auditors would say, okay, we'll schedule you 2-3 months out when we're lucky, and they need a code freeze. Whereas formal verification, we can just keep updating and updating as we go. In the bear market, I think we'll probably switch to a 6-month audit cadence because it's now easier to schedule. And it's not like, oh, we need a code freeze right now to schedule you in 3 to 6 months. It's instead more of like, okay, yeah, we can get you in, 8 weeks later and give us a code freeze 4 weeks from now. So the period we need for a code freeze is much smaller. Mm-hmm.
More questions?
So given that you have this process,
Yeah.
Yeah, so given that you have this process where firstly your architecture is very modular, the scope of things is relatively small, and you make your engineers think about it very formally by writing the specifications as you go along, does Certora often catch bugs for you?
Does it offer what?
Does running Certora with these specs actually often catch bugs for you guys?
Interesting. The first thing it does is it forces us to, so typically I mentioned that cycle where we'll go through, where we'll write the formal verification logic at the end and then go and update the implementation logic. So the first thing that Certora helps us catch is usually if the spec is really hard to write, we probably have not written good code. So when it's hard to write, we'll then go back and we'll change it. So then when the spec is easy to write, then it essentially, it's then the most cases where it catches bugs, interestingly, is not when we're working on a particular piece of implementation logic. So usually for example, like if we're working on implementation logic and we're working on a spec alongside it, usually it's not catching bugs then, it's more help in guiding our architecture. But when we're modifying parts of our code base that Siri wants to learn about formal verification too. But when we're modifying parts of our code base that might touch a lot of modules, that's when it catches bugs. So that's what's very interesting. It's like tests, you'll write it, and you'll typically catch bugs on the code you're writing. With formal verification, you'll write it and typically catch bugs on the code you're not writing right now. So yeah, that's been fascinating and very useful.
Yeah, this is a really interesting question. This is bugs, how many bugs you find in formal verification. So I remember in the 2000s we used software modeling, which is like a role-based testing at Microsoft extensively. And it turned out that the discovered number of bugs by the testing teams went down. And that was really frustrating, because I mean, what's happening? And, so like we then argued and tried to show, and we were able to show it's because it prevents bugs in the first place. It's a different way of engineering, but it's hard to sell to conventional engineering teams.
Absolutely, yeah. When we started adopting formal verification, the number of bugs that we saw day to day went down, and the number of bugs that audits caught went down dramatically. So yeah, it's very much, if we were measuring the success of Certora by how many bugs it caught, it would not be the best measurement. Instead, if we're measuring it based on how many bugs that don't emerge at any other part of the cycle, it's very clear. But it's a little more indirect, so sometimes it feels a little weird of like, oh, I'm spending all this effort writing these things and it's not catching anything. And it's like, well, that's kind of the point. Like, it's not catching anything because it's made your code better.
So do you know how many bugs it needs?
I hope none. But that's the beauty of it, is I know the states that are reachable and not reachable. So as long as we're good there, we have it very robust. Yeah.
No, but maybe major things that auditor found after your formal verification?
When we've done audits, we have very rarely had issues after adopting formal verification internal to our contract. It's always been issues with other contracts. For example, like we had an issue that an auditor flagged where that basically we were not accounting for ERC20s that took a fee properly. We were accounting for the pre-fee value and not the post-fee value. And that was something where there's a small number of contracts that have fees. There's a small number of contracts that don't have fees turned on but could turn them on in the future, like Tether. Read into that what you will. That was what the auditors caught. So if formal verification misses anything, it's typically essentially contracts, like interactions with other contracts. In the future, I would love if Certora had like a library of like, here's specs for interacting with Oracle contracts, fee-based contracts, et cetera. That's something that I think is something that right now we can basically show the auditors, hey, this is like, focus on all the external contract interactions because they can read the spec files and have confidence in the internal contract interactions.
More questions? Thank you, Will Pepper, for
Thank you so much.
fantastic talk.
Thank you. Cool. I'm also available at will@syndicate.io or at willpapper on Twitter or Telegram if you want to chat. I'll be around here hopefully later today after some calls. Thanks so much.
Thank you very much.
Thank you.
Thank you.
What?
And the lapel mic back.
Oh, I'll give it up there. Yeah.
So, okay, most of you, it sounds from formal verification. How many of you are familiar with Certora? Okay, so so Certora is actually an initiative, a one-person initiative, a one-man show, but a very interesting one-man show. So basically, Rajiv, he used to be a security researcher at Trail of B, and then he's run his own show to basically teach people about Ethereum, solidity, auditing, formal verification, everything. And he's actually done a fantastic job. Actually, if you see a few of the key developers at Sushi, many other places come from his teaching. And one of the things that he has done together with Certora, he has done a boot camp for teaching formal verification. There's another one going now. And from the first boot camp, actually, Certora got quite a few fantastic people. Two of them are here, Armen and Yufei. So Armen will speak about how formal verification is used together with Code Arena. Please start.
Yeah, go under Apple thing to displays, and then arrangement.
All right, hello everyone. My name is Armen. I think I introduced myself already, security engineer at Certora. I'm going to be talking about crowdsourcing formal verification. We recently had the first ever formal verification contest with Code Arena and BlockSwap. It was really cool. We thank you to the BlockSwap team and Code Arena for helping us arrange everything. Definitely a cool step to take and something to be a part of. So I can first talk about maybe audit contests. Some of you might be familiar with them, some of you not. Traditionally, you have someone spend some time looking at your code. Audit contests allowed a crowdsourcing of this process, and has been something very valuable for many protocols. You put up some amount of money, and whoever finds the rarest and highest severity bugs gets a higher percentage of that money. So with formal verification, there's a lot of protocols that like to formally verify their contracts, but they're not experienced with formal verification, and maybe it's out of their budget, or they don't have the time to gain the experience. So we thought maybe crowdsourcing this could be something that's useful. So to do that, we had to come up with a slightly different incentive model, because when you formally verify a contract, you might have properties that don't necessarily catch bugs, but they add coverage and they prove the lack of bugs. And in the future, they can catch bugs if you're running them in your CI. So here's kind of the incentive model we went with. You could see the reward distribution. Real bugs were rewarded 55% of the bounty. Injected bugs, which we used to check these properties that added coverage but didn't necessarily catch bugs, got 35%. And we also gave a small portion, 10% to participation, which is just basically an easy thing. And we see this as an investment in the community's education and upskilling researchers to add further value to protocols in the future. So after the test happened, we had a process of rewards and submissions. So each researcher had a private fork of the repository they were working on, and the submission was just a PR from one branch to another. And what we did was we integrated CI to automatically inject all the bugs and test their properties. So we were able to calculate rewards very quickly and get the rewards out to researchers, which I'm sure they're happy about. And you can see here as an example, what you want to see is your spec passing on the original, unless you're catching real bugs, and then failing on the bugs that were injected that you didn't know about beforehand. So this will tell you when you submit whether you did good or not, based on how many violations you see. And then the normal bugs were reviewed by a judge, which was me. But in the normal style that audit contests usually have, you talk with the sponsor and the warden and try to get a fair outcome. So here's some highlights from the contest. You can see a lot of people registered. A good number of them started. 32 people submitted something. 26 of them caught at least one injected bug. 21 got rewards. We got over 600 properties written. 5 bugs were caught, and only by 6 people, and so most of them were unique. So we got a lot of increased security for the protocol. And we, BlockSwap through Code Arena gave 30,000 in rewards to all the participants. So now I'm going to kind of give you an overview of the contract we looked at, why we chose it, what it does, and then I'll walk through some of the properties that were implemented, some of the properties that caught bugs, and maybe the future of what this might look like. So this is BlockSwap Syndicate contract. It's part of the liquid staking network that they've built on top of Stakehouse. It's a small contract, but it is very important. It handles the distribution of fees and MEV. And if we zoom in here, you can see it takes, it basically distributes, it's responsible for distributing the rewards for some of the stakers and also the node operator. This whole protocol basically allows node operators that don't have enough money and people that have money but don't want to be a node operator to work together to be able to help secure Ethereum and also earn the rewards that gets you. So you can see it's a pretty complex protocol, and we chose this piece to start with for the first formal verification content to make sure that it goes quickly and to ensure that people are able to understand the contract and
So,
not necessarily easy to guarantee, but you know, we had people that were able to prove it, so that's good. And then we have different types of solvency rules. You want to make sure that all the stakes up to the total, so you don't have any like missing money and super echo.
Was it echo?
Yeah, so you can see some of these properties. We had not, the claimed rewards must be less than or equal to the total claimed rewards should be equal to, but I think a typo. But yeah, you can see maybe this first rule I can go received before, you call some function, you check the received after, and you should it should only increase, right? You should never have this decreasing. And if you have it decreasing, there's probably something going wrong in the protocol.
Do you think the handle's loud enough?
And these are all written by researchers, and some of them had just started learning the tool when the contest started. It was a 2-week contest, so it was really cool to see that people can just pick it up and start proving properties and adding value to this protocol right away. And then you can see 2 invariants at the bottom. I don't know if you can read that, but these are also kind of interesting solvency. One is a solvency invariant, and the other one is also a solvency invariant. Here's the property that.
Those are muted. Yeah. Yeah, we're gonna put another lob on there. We just had a battery blow out, so we'll just put another lob on and start that off.
A bug in the code. You could see kind of a quote from the person that wrote this. Sweet, thank you. Yeah, so the process this person used was to go through the documentation, understand the contract, look through the code a little bit to understand the properties, and then implemented this and found out that it didn't actually hold. So what this shows is that you can have a validator that's not actively validating, and you can have a staker that can stake for this validator, right? And the staker will also earn rewards even though they're not risking any of their ETH, which usually they would. So this is actually not a super severe issue because every other function that you can interact with on the contract makes sure that if validator or not is inactive, it gets deregistered. But in the stake function, it doesn't check that. It only checks if it's deregistered. So you can have someone staking for an inactive validator. So yeah, this was a very interesting property they wrote and caught an interesting bug with. So this is kind of, I'll go through some of the methodologies that we asked some questions to the researchers and to see how they were using the tool, what they were thinking. It seemed like a lot of the people that were starting out were just auditing the code and then using the tool to have like a proof of concept, a concrete example that it gives you. And this worked well for many people. There were some people that caught real bugs using this method, and a lot of the people were able to get the participation rewards at least and catch some injected bugs. But the top performing researchers were able to, they took a higher level view of the contract. They read the docs and thought of properties without necessarily looking for the bug themselves, just thinking of high level things that should be true and implementing them. And this is kind of like a little, we say like, don't read the code, just implement what it should ideally do. Because if you read the code too much, you can write spec that verifies that all the bugs in the code are also in the spec. So it's, obviously you have to read the code a little bit, but yeah, if you're like that guy, you only read the docs. So overall, I think it was a very successful first contest. There's some difficulty with compiling all the specs into the one master spec, but I think as we automate a little more and have stricter guidelines for documenting people's spec, this is going to get a lot better. But everyone in the community seemed very excited and happy to be participating. This is some guy that loved our tool a lot, Zapas from Cradium. There's a lot of people really excited about formal verification contests. I think it's a cool opportunity because you get to participate, learn a new tool, upskill yourself, and also earn awards and protect the protocol, not just today, but also in the future. So you're building kind of an infrastructure for this protocol that can be used as they continue developing new contracts. And so I think that's my talk. I would love to hear any questions you guys have or ideas for.
Yeah, could you, we have a mic, and could you repeat the question also for people online?
Sure.
So this is really cool stuff. So maybe I didn't got that in the beginning when you talked about incentivizing this effort. Is that basically an application on a blockchain, how you do this? And then
So this is the question. I think it was clear, right? Do I need to repeat it? Repeat. Yeah, the question is how are we incentivizing it, and whether the incentive structure is on the blockchain. It's actually through Code Arena. Trey from Code Arena is here. What they do is they have a platform. It's a Discord. If you're a sponsor and you have some code that you want to improve the security of, you can put up some bounty, X dollars, and then you have some timeline. So for some number of days or weeks, people can look at your code and submit bugs. And then at the end, there's some calculation on who gets the most rewards. It's not done on the blockchain except for the transfer of the funds, I think. And it's based on, if you have a high severity bug that nobody else found, you'll get the most rewards. And all of this pool is guaranteed to be distributed. So it's just based on who adds the most value to the protocol, who finds the biggest bug. And so we kind of took that model and applied it to formal verification with a slightly different incentive. It's not on the blockchain, usually mostly on Discord, audit contest. I think that answers the question.
Hey, can you hear me? Yeah, first of all, I think that was a fantastic competition, so thank you for running it. And do you know how many of the participants, especially those that actually won prizes, had some former experience with formal verification?
There was a few that did. I know some of them have participated in previous Certora competitions, but I know there's many that didn't. I think one of the top 5 performers had no previous experience and started using the tool. So we made the tool available 2 weeks before the contest started. I think he started using the tool when the contest started. So he had exactly 2 weeks to both learn and implement properties. And I think he implemented a property that caught a real bug. And there was other people like him that were learning the tool for the first time. There were many that hadn't done an audit contest before. So it was a lot introduction to many things for them. But I'd say maybe, I don't know, just guessing, like around 50-50. It didn't seem like everyone was experienced or that no one was experienced, but there was definitely a group of each.
And a follow-up question. do you see any correlation between the success of individuals in other code arena security competitions and the formal verification competition, or that's like a completely separate skill?
I think like if you can, I'm sure there's some correlation, right? But I don't know exactly everyone's background. I know some of them have participated in other contests and they've done well. A lot of them were beginners. A lot of the people that can think of good properties, I think, can be good auditors and can be good formal verification engineers. So there's definitely overlapping skills, but you can kind of maybe you're good at thinking of properties, but reading through code line by line, you get confused, or you can read code line by line and have muscle memory of catching bugs, but then when you zoom out, you can't think of like the high level property that it's breaking. So I'm sure there's some overlap, but you know, some parts are distinct, I'd say.
Thank you.
So do you think that 2 weeks is too short or too long for content?
I think for the first one, it was a good time. Depending on the experience of the community, it could be too short for this type of contract. I think a lot of people were going through the tutorials during the contest and then getting into it. So it's good for like an introduction, good for the first one, but in the future, for simple contracts or smaller contracts, it could be shorter. But I think for this one, it was a good amount of time.
More questions? Let's thank Armin again.
Thank you.
And we have a 10 minutes break now. There's coffee, there are things.
Thanks for your patience. Yeah.
Check 1, 2, 2, 2, 1, 1, 1, 1, 1. Check 1, 2. Check 1, 2. Yeah, we're just gonna kill that one, and we're gonna use this one because this yeah this takes care of that. Okay, so now we have it. No, I want him to use the good lav that you.
This.
Okay, cool. Sorry, last question. I saw you have some of those like clicky things. Oh yes. What tab the USB dongle? Excuse me. That's my fault. I forgot to pop it on. It's right here. That's let's. So it looks. Okay. He wants to test. Let me work this out. Yeah, go work. Testing, testing. Is this working? Is this working? Okay, sounds good.
Check.
Let's do like a 2-minute warning and.
Okay, we're going to start in 2 minutes, please.
And when you talk,
What do I do? Like this?
that's perfect. But you see this button? Let me just go ahead and talk. Hello? Just count. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm good? Let's try to say something again. Okay. 1, 2, 3, 4, 5. All right, we're going to get started again here in a minute. So if you could take a seat, and Muli is going to introduce the next speaker. Excellent. Oh. Huh.
Maybe you can take a seat, Leo. Maybe you can take a seat. No, sit down. Yes. So actually, this is actually the first technical talk. The first two talks were less technical. Now we're going to have a technical talk, and it's about verifying Cairo. We are very pleased to have Julian here. So Julian also has a formal verification background from Imperial College, one of the best schools in this place, under Philip R. Gardner. Yeah, should say that Nethermind is one of the key players in the area of zero-knowledge proof. They have been recently, or not so recently, but they have converted Uniswap code into Cairo. They have developed unique technology for compilation, and today is going to talk about their formal verification tool.
I'm good? Okay. Great. Thank you so much for the intro, Muli. So, yeah, I mean, I'll caveat that by saying it's as technical as a half-hour talk allows, right? But yeah, so as I said earlier, there'll actually be 2 versions of this talk. This will mostly focus on, hey, what are the interesting verification challenges when it comes to Cairo? And then a very, very quick high-level overview of how we actually succeeded in doing that. Tomorrow, I'll actually show you how to use the tool if you're interested. So, yeah, and as I said, tomorrow the talk is actually at the Certora event. Sorry, not the Certora event. The StockNet event, my bad. And so there I imagine that one of the key questions I might get is, hey, what's a formal verification tool and why do I want to use it? And I'm going to give a talk where I'm going to use the quote that Muli used earlier from Edgar Dijkstra and all of this, right? But obviously you guys already know all of that. And so I'm going to focus more on the question you guys probably have, which is what's StockNet, right? So we're going to start off with that. So at the high level, it's an Ethereum L2. It's a ZK rollup that uses stocks to be able to produce proofs of computational integrity. And they can then be checked very succinctly on the L1, and this provides a bunch of scaling advantages that you probably no doubt already know about a bit. So one thing that's interesting now from a formal verification perspective is that the bytecode, which is called the Cairo bytecode, which runs on StockNet, is somewhat unusual. It has a few unusual properties which are designed to make the proof verification and generation as efficient as possible, but obviously makes the job of writing code for it and verifying it a little harder. And then finally, as Muli already mentioned, we also have this warp compiler. One interesting thing about StarkNet is there's this warp compiler that we've developed at Nethermind that compiles Solidity directly into Cairo. So if you have a Solidity contract already, well, you can get all of the benefits of StarkNet essentially for free. Okay, great. So that's StarkNet at a high level. So, well, what about this bytecode? So what I mentioned, there are some unusual things about it. The first thing is that it's a non-deterministic stack machine, right, which is a little bit unusual. You can have essentially non-deterministic jumps, and you have to think of the prover as essentially traversing all possible paths that are possible there, right? It also has a very small instruction set, which makes things easier, essentially. So you have assertions, calls, returns, jumps, and being able to increment your allocation pointer. So that's the pointer that points to the head of your stack. You also have a frame pointer and a PC, as you do on most stack machines. The next thing, which is very unusual, is the memory is read-only, essentially. We just generate constraints on the memory, and you can think of the memory as being non-deterministically chosen before the execution, and the program itself is just checking that these constraints are satisfied, right? And yeah, that actually is, well, we'll talk about it a little bit more a bit later on, but I think actually that is generally an advantage because mutable memory makes things a lot easier in a lot of senses. Next, our primitive values are felts. So these are field elements from this specific field. You can check that's a prime number. And obviously that in terms of formal verification, that is a bit of a disadvantage because it essentially blocks us from using a lot of standard methodologies, which you can use for like UN256s, like bit vector theories, these sorts of things, right? So that caused some interesting issues and has meant that we've mostly had to focus on using nonlinear integer arithmetic theories and SMT all this. We'll talk more about that later. Finally, you might think, given that, given the simplicity of the language, you might think, hey, this sounds like a bit of a Turing tar pit, right? So everything is possible, but nothing is easy. And you'd probably be right if it weren't for built-ins. So built-ins are essentially a way of extending the Cairo and StarkNet smart contract languages with some extra capabilities. So there are these things like there's this range check built in that helps you check that some felt is less than 2 to the 128, and these sorts of things. And they're all things that would be computationally possible using the Cairo language, but very, very inefficient, right? And so essentially what a built-in is it's an area of memory which has extra constraints on it. And so, for example, for the range check, you just know where this area of memory is, you write something to one of the cells, and if it's greater than 2 to the 128, well, there's an assert failure and your program reverts, right? And you'll notice there are some dots where, because there are a bunch of other built-ins, very conveniently, I've included all of the built-ins we don't have support for yet. So if you want to ask me more about that later, please feel free to do so. Great. So yeah, I wanted to give some examples a little bit, and apologies, the slides are not very colorful. There isn't yet very good syntax highlighting for Cairo and StarkNet. I'll work on that at some point when, yeah, I'm a little bit less busy. But yeah, so this first program here is Felt, is meant to sort of show off, well, two things. The first thing is it shows off a non-determinism. So I think this has a laser on it, doesn't it? So we have this jump here, which jumps on if essentially this area of memory at AP at the top of their allocation pointer is not equal to 0. And we have absolutely no bounds on what AP is. So essentially what happens is you can think of this as exploring both possible paths. And then we have an assertion that will fail if we weren't meant to be exploring that path, right? So here, the path where it doesn't do the jump is a path where we know that A is smaller than or equal to B, and we check it with this assert here, which will fail if that isn't the case. And in the not less than or equal to, we check then that B is less than or equal to A, essentially, right? And you might say, well, computationally, that sounds pretty terrible. And you'll, oh, wait. There you go, sorry, wrong direction. And this has actually helped out with this little thing that some of you may have noticed here, which is what is called a hint in StarkNet. Essentially, it's a way of resolving the non-determinism, telling the solver, oh, actually, you should be exploring this path. From a formal verification perspective, we want to completely ignore these, right? The reason being that the computation integrity isn't checked on these. This is just essentially Python. It's whitelisted, so you can't run literally anything, which is good. But obviously, we can't check that individual solvers will actually run this hint. We have no proof of that. And so essentially, we want to assume that the hints aren't run, and that even given this, the program is correct. Cool. So that's one thing. Another thing you guys might have noticed is this known AP bit change annotation on the function here, and this thing of why am I incrementing AP for no reason, apparently not using this, right? And the reason is, well, it turns out that there are some disadvantages to a stack machine in the context of read-only memory because, well, it turns out that when you call a function, you can't just revert your stack back to the original address and then everything can continue with the return values as if it were as it was before, right? Because all of that stack has now been consumed, essentially. And so if you have a program like this at the bottom, where say f doesn't have a known AP increment, and then, I don't know, you define some value in the middle, and you have some new function here that does an AP increment that you can't know statically. After all of this, it's essentially impossible to know in the stack, statically at compile time, hey, how far do I need to go back to find this x value, essentially, right? And so essentially because of this, it's good to be able to have, for functions to be able to have fixed APs, and this is something that we need to be very careful in not abstracting this, and being very careful in keeping this information when we're modeling the code, because the actual correct functioning of the bytecode depends very, very heavily on this. Great. Cool, okay, some other built-in examples, once again, these are some weird semantics for built-in. This is pretty heavy, apologies once again, but we'll look at this first one. So this is just a function that takes some input, which is a felt, and it writes it to this range check pointer. That's that area of memory which checks that anything written to it is smaller than 2 to the 128, essentially, right? And here's the interesting semantics here, which is I then need to update this range check pointer. And you might notice this is essentially an implicit argument. It means I take that in from this argument in implicitly from the caller, and then I pass it back to the caller, and it's implicitly updated, essentially. If I don't do this update here, I don't update the value of the range check pointer, I just write this, the semantics don't actually require that the range check occurs. And so there are some extra semantics there that we need to think about carefully in terms of making sure that actually all of the built-in pointers are correctly updated. And then finally, very quickly, this is just an extract from a toy AMM example, which is given as part of the StarkNet, like the basic StarkNet tutorial. And in particular, it has a storage write. And so we have a storage memory, which actually is mutable. And so there is some mutability we need to model there. OK, so those are a few of the interesting, like basic and some of the more interesting, I guess, challenges of verifying StarkNet smart contracts. Yeah, sorry, I forgot to move through the highlighting. OK, so now I've talked about StarkNet quite a bit. What's Horus? So Horus is a form of, like an automated form of verification tool, and it's meant to have a relatively low skill ceiling. It allows essentially developers to annotate their smart contracts with, the functions in their smart contracts with like pre and post conditions which have Hor-style semantics, right? So essentially we say, given that the precondition holds and I execute it and it terminates, then this must hold at the end, right? So, so essentially we have a very simple workflow that allows us to, we have this Horus compile tool, which you can run your annotated smart contracts with it. It generates both a binary and a specification file. And then we have the second part, which is written in Haskell, which is Horus check, which essentially takes your original binary and your specification file, and it combines all of this into essentially a bunch of SMT queries, which we then discharge, right? Okay, so this is the very, very high level. Apologies, I am not a master of ticks. You'll probably immediately realize that from looking at this diagram. This was pulled together a little bit quickly, but there you go. So yeah, so this sort of shows this workflow, right, where you have Horus compile, you have your StarkNet binary, which you can then use and run on StarkNet, and you have your spec file, and we have Horus check here, which does a couple of interesting things. I'll go through the the pipeline quickly, and then we'll go through very quickly a little bit of what are some interesting parts in different parts of this, right? So we have a CFG generator. So we generate a CFG of your StarkNet binary. We annotate that CFG with essentially invariants that need to hold at various points, branching conditions, these sorts of things. We then have what we call a module splitter. Essentially what this does is it takes a CFG, traverses it, and finds essentially all linear subprograms. So those are programs that will go from like one control flow point, one entry point, to another that have pre and post conditions annotated, and we get a module from that. So a linear program with a pre and post. Very straightforward, right? We then have finally constraints generation, where we convert this into a bunch of constraints, and that is then finally converted to an SMT query, which we can discharge to a bunch of backends, right? So fairly straightforward. So here are some interesting parts. As I said, limited time. How am I doing time-wise, actually? Okay, not too bad. Still some time. Essentially, the first step, which is a little bit, as I said, a little bit interesting, is the CFG generation. We insert some standard specs because obviously, sorry, actually, maybe I should talk about inlining first. So we have this fairly straightforward capability that essentially we don't want our users to have to write specs for every single function in the standard library that they have, right? And that would also put a very high load on Starkware if every time they modified their standard library, they needed to potentially change the specs, etc. That potentially puts a lot more weight on them. So we have this capability to inline things, which is done at the CFG level, where essentially if you have a function call to a function which doesn't have very complex control flow, it's limited in the complexity of the control flow it can model, but we essentially just inline those semantics into the into the functions which are calling it. We also have some optimizing edges. I was talking to Grigore actually just earlier about this, that it's one issue with a lot of, like, I guess, SMT-based automated solvers is you essentially end up with these huge queries which aren't chunked at all. You throw it all at a solver, and if it breaks, you have no idea what went wrong, right? And so this is our attempt at trying to get there, where essentially we take individual like functions and we split them up, essentially checking individually, having checks for the precondition of different functions which are called and these sorts of things. And so we sort of, it's not incremental, so it's not SMT incremental solving, but we have like incrementally breaking up these modules, and so to be able to get a better idea of where there is a solving issue if there is one, right? And then, as I said earlier, we have some standard specs which are injected. So these are, we have built-in specifications for some of the standard library functions, which just because, abstracting functions is good, right? It helps you speed up solving and these sorts of things. And once again, we don't want to put so much of a load on either Starkware or the users in terms of this. And as I said, we'll talk about this a bit later, but in the future, I think we'll take more of a Certora-like model where we have a separate spec file rather than having annotations in the source, and that will make this sort of stuff a little bit easier and a little bit more configurable, right? So we then have the module splitting, which I talked about earlier. It's not too interesting. Then we have the constraints generation for each module. And as we mentioned, we have, we have this immutable memory. And when we were first doing this, we were actually modeling it with UF-near, so uninterpreted functions to model in our SMT theories, to model the memory, and near to do all of the arithmetic in our programs, essentially. And about a year ago, I was at DevConnect, in Amsterdam, and I met Mully, and he told me one key issue here is near, obviously undecidable theory in general, just doesn't compose very well with other theories. So really a priority for you guys should be to try and really minimize the number of extraneous theories that you use here, right? And so we use some fairly simple methodologies essentially for, while we're generating the constraints, removing any references to memory accesses and replacing them with just like in a straightforward way, right? A value and an address. And then we have, when we generate the queries, we essentially generate for each possible memory access, we generate, we look at essentially all possible pairs, and we say, hey, if the addresses are equal, well, the values must be equal. It's quite straightforward, right? And so yeah, so when we do this query generation, we do all of that. Most of the time, actually, we get quantifier-free near. In some very restricted situations, we do need near to, so be able to have some limited quantifiers, actually just existential quantifiers specifically. And actually, thanks to that, I think that we've gotten really remarkable performance with specs which have nonlinearities in them, right? So I mean, if you guys have played with like SMT solving based form verification tools, things like SolCMC, obviously not Certora, but things like SolCMC, which aren't quite as developed, as soon as you have the product of two variables in your spec, you're dead. It's not going to prove anything, right? This is not going to work. And so we've actually been able to do, and we'll talk about this in a little bit, we've been able to do a few actually pretty interesting nonlinear examples. Cool. Finally, we have some we optimize these queries using a bunch of Z3 tactics, which honestly to this day is still a little bit black magic to me. And that, oh, sorry, just dropped that. Sorry, 1 second, guys. Ooh. That's okay, I think I got it. Cheers. Which, as I said, yeah, is still a bit black magic to me in that essentially I met Niklas Bjorner once again at the same event. He looked at some queries we wrote and he was like, here's 3 tactics, always use those. And we have, and it served us incredibly well. So there we go. That guy's, yeah, incredible. And then finally, obviously, we discharge all of these to SMT solvers and cross our fingers, right? Essentially, that's sort of how this works. Great, so now a couple of conclusions. So as I said, I think that Horus, for an SMT-based form verification, an automated SMT-based form verification tool, is actually pretty powerful. As I mentioned, we can do some interesting nonlinear specs. So in particular, we have a toy, oh, that's actually kind of wrong, a toy, specifically a constant product market maker, right? And so this is one of like what do you call it? One of the, it's part of like this toy MM is part of the tutorial, the basic like StarkNet tutorial. But as I said, it contains some nonlinearities in the specification, and certainly if you look at a lot of other solvers and try and specify something similar, it will fail on the functions which have significant nonlinearities, and we're able to do that. We've been talking with Maker, who've obviously been porting their work to StarkNet, and they had some parts of this VAT contract, which once again had significant nonlinearities. And we were able to pull that off. Well, we had to do some slight simplifications, so I put simplify that. We had to do some slight simplifications to the function that they wanted us to verify, which had these nonlinearities. But we were able to do so in the end. We were very pleased with that. As I said, Horus has a low skill ceiling. You guys saw these specs are essentially like just written in a slight extension of the StarkNet assertion language already, right? So pretty straightforward. And yeah, so that's Horus overall. So what are we going to do next? Well, as I mentioned, we want to have these separate specification files that will make things easier in terms of being able to write specs for the standard library, etc. We also want to have primitive int256 and uint256 support, obviously super important in the Web3 DeFi space. It's a very commonly used data type. And for the moment, we can sort of reason about them, but the specs are extremely unwieldy because how they're implemented. You may have noticed that the prime number that is the base of our field is smaller than 2 to the 256. So these are implemented as 2 felts, which most must be both smaller than 2 to the 128, and there are all sorts of like bit chunking and things like that happen. So in practice, not so easy to reason about. So we want to put in some primitive support. And then you guys might have heard about Cairo 1.0. So there's been a new language release with some significant changes. And we have a lot of different thoughts there. One thing that we could do is just create a new version of Horus compile, which gives us our bytecode. Cairo 1.0 also now is a much higher level language. And we might want to, it has an intermediate representation called Sierra. We might be able to benefit from reasoning at that level. We'll sort of see where Sierra goes. And then a couple of moonshots here, which are things I'd really like, but I'm not sure we'll realistically ever have the time to do, which is obviously is a lot of things in full verification. But obviously we want some other backends, because I think Leonardo, we saw a quote from Leonardo Demura about nonlinear integer arithmetic, saying, you know, SMT solvers are great at nonlinear integer arithmetic, but Mathematica just blows us out of the water, right? And so since we can do mostly only NEO, we were thinking maybe, you know, Mathematica backend might be interesting. And then this other thing that we have is Some of you might have heard that Jeremy Avogad from CMU has developed a formal specification of Cairo, essentially. And we've been working with it quite a bit. In fact, we worked on formally verifying parts of the ZK-Lend StarkNet protocol with it. And in particular, we've been thinking of essentially using its semantics, these semantics to essentially create a property test against a formally verified semantics of Cairo for Horus to try and be as sure that we've got we're as bug free and have as much coverage as possible, essentially, because at the end of the day, with automated theorem proving tools, there's always the issue of like, oh, how are you sure that the semantics of the queries you're discharging this to are correct? And the answer is, I got some engineers to look at it really carefully. And often that's not good enough, right? So that we're hoping to hopefully boost the security considerably of Horus using that direction. Great. Cool. So I think that's everything I have to say. You can try it yourself. If you want to come to my talk tomorrow, you might see me use it. Let's see how it goes. And then finally, obviously, you guys can keep in touch. That's my Twitter handle. That's Nethermind's Twitter handle. And this is my email. Thank you very much. Oh, OK, Grigori.
So I wonder, did you have to deal with any zero-knowledge stuff, like snarks, starks, or anything like that? Because so far looks like a normal language.
Yeah, completely fair. So the answer is, at the level of Horus, right, Cairo creates an abstraction where, OK, the language is weird, but I don't need to know too much about the underlying ZK methodologies. But once again, we've worked with Jeremy's formalization, and there, yes, the answer is absolutely yes. But yeah, sort of disjoint from Horus specifically. Oh, go ahead, Efra.
I'm looking at, my knowledge of zero knowledge is very zero, but
That's okay.
I'm looking at these things. I know they generate some sort of constraints that becomes a circuit that's validating things on chain. They generate some execution. That's the off-chain code that produces the thing that's submitted on chain. Your pre and post conditions are constraints, right? So could you include those constraints in the circuit that's generated and enforce that your pre and post conditions are being held on chain, even if the off chain code is computing? Like, it could just reject everything that is not holding in that pre and post condition.
Sure. And yeah, I mean, you can very straightforwardly do that because, as we said, the assertion language is a slight extension, which you can easily create some extractions into Cairo of these assertions, and then essentially just chuck in asserts at the beginning and the end, right? Yeah. So yeah, you could absolutely do that. It's not something we've done yet, but we have considered doing that as a very simple, just to create a backup. So even if Horus is wrong, at least your code will.
It won't accept things that don't.
Exactly.
Aren't in the property.
Right? Yeah. So we are considering, we will be doing an extension to do exactly that, actually. Yeah.
Hi, thanks for the nice talk.
Thank you.
So I have a design question. So you said that one of the next things that you want to do is have a separate spec language.
Yes.
And I'm wondering why. Like in some ways, having annotations in the program itself can also be kind of convenient, right? Like you don't like. I know at Certora we have a separate specification language, and I think that's one way to go. But I'm just curious. Why do you want to do that?
So I think that the main reason, and we might go for some sort of hybrid approach, right? But the main reason is just preventing users from, because for the moment, if you have a standard library function, which is a bottleneck on your blocking, our solution for the moment is stop importing it, copy and paste its implementation into your code, and then put in line specs, right?
Yeah.
And so I think you're absolutely right that there is a visual aspect to it, and to be able to see the code side by side with the specs a little bit, and that's probably a good thing. And so we might definitely go for, we'll see. We might well go for a hybrid approach essentially. But I think really for the standard library and for the ease of issue and for the ease of use, being able to have at least the possibility of loading specs from separate files might be pretty useful.
Okay, thanks.
No worries.
So I have two questions. One is that you're saying you are using 3 solvers.
Yes.
Which one works the best?
It depends on what you want to do. So in my experience, for very, very big but simple queries, CVC5 works best. MathSat is head and shoulders above the rest for nonlinear specifications, right? And Z3 is the most consistent in a sense, right? So it's not head and shoulders above anyone in anything, but it covers the most of the specs in our testing infrastructure, but it's often slower than the other solvers.
I see. The next question is actually the same question you asked Will. How many bugs have you? I mean, it's actually especially because your team also is doing auditing for Cairo, right?
So no, we're not. But there is a separate team at Nethermind that is doing auditing for Cairo. Yes.
Are they using your tool?
So they're going to start doing so. They're going to start doing so. So we've already done some workshops with them and these sorts of things. And yeah, I mean, we've already, so one like small bug, wait, did I leave that example in? Yes, yeah. So one small bug that we did catch in like a pseudo-practical example that the team had come up with, and this was actually, so the auditing team had come up with, and this was actually why I gave this example, was this example, which you might notice without the precondition of token 1, essentially, you can have some behavior that you might not expect here, right? Which is essentially the spec should be, well, token 0 implies return 1, or the return t is 0. And so essentially there was a case in some some like AMM that dealt with multiple possible assets where there was an issue where there wasn't sanitization on the input to a similar function to this, which was meant to find like some pair in a trading pair, and it would under certain circumstances, because of that sanitization, give an erroneous input. But once again, I mean, these are they're still somewhat synthetic examples in that they're things where the auditing team came to us and they were like, well, we know there's a bug here, and they were able to write. So in terms of like real world examples, where we released the alpha a couple of weeks ago, and we're hoping to find some soon, but and we'll keep you updated on that, Muli.
Thanks. And about version 1 of Cairo, how difficult would it be?
So as I mentioned, right, there are two different approaches to this, right? The first one is just rewriting Horus compile, and we compile down to the bytecode, we get the same specs, and we use the Horus check state, essentially. The core checker remains the same. The other, and that we suspect would be relatively easy, so it would take, maybe a month or two to be able to make those changes, tops. And then there's the possibility of changing the core solver to reason at the level of the Sierra intermediate representation. And there, I'm not sure I can answer that question right now. Probably a lot more time. So given that it took us already, 6-7 months to write already the core solver for the bytecode here. So yeah, some time.
Okay, thank you. More questions? Thank you very much again.
Okay, thank you very much.
So the next speaker is Everett
I imagine.
from runtime verification. We all actually know Everett. Everett did his undergrad in physics in Urbana, right? And then continued his PhD with Gregory, but didn't finish, no? Not with you? Yeah, and he's actually one of the earlier guy in this space. Done actually interesting work for Uniswap auditing, maybe, no? Uniswap V1, yeah, like this is actually how I started to learn about this space, and he's a key player in the K and its users, and now he's going to explain.
Hopefully the computer obeys. And then I think I need to set up my proxy server again. Okay. So I'm going to be giving, yeah, sure. I'm going to be giving a talk that probably many of you guys have seen fragments of in the past, and I also gave a similar talk at Certora. They invited me to speak to the engineers there, which was very nice. All good? Or?
This is for the remote.
Okay. I'm okay. Sure. If I can figure out how that works. No. I think I'm good. Thanks. So yeah, you guys have probably seen lots of similar talks from me. So there will be some new stuff. I'm going to be showing off some UI stuff that we've been working on with the K framework, and some other things that we're hoping can bring it into feeling like a modern verification tool, as opposed to something that is hard to use and hard to adapt to. So this other talk I gave at the Certora workshop, you can just find it on Certora's YouTube, is kind of the first half of this talk, which I'm going to go through a lot quicker. And then following that, I'll be talking a bit more about some announcements that we're trying to make here, so how we're modernizing K, making it better. But I am going to go through the first part for completeness, but much quicker than I did before. So what's K? So K is an operational semantics framework. That means that you can specify your programming language in K, and then you get a bunch of tools derived from that specification for free, quote unquote. The nice thing is that you have the shared semantics between all your tools. You can have high assurance that your model checker is agreeing with your compilers, agreeing with your interpreter on the semantics of the programming language. There's a logical formalism underneath it. It's called matching logic. Matching logic has a lot of very nice results about it. Lots of papers published about this. Highly recommend you check it out. It definitely is a modern logic to use for doing these things, and in my opinion is much better than a lot of the higher order logics that people like to do proofs in. And then architecturally, K has two main backends. I'm going to talk a little bit about some architectural changes that we're making to K to kind of dissolve this idea of like, oh, it's just concrete execution or just symbolic execution. And then almost all of our tools are powered by K. If you go to this website, kframework.org, there's a couple tutorials there on how to use K, which can be very helpful. So this is the problem K tries to solve. You have, for every language and every tool, you have an arrow here. This is like CBMC right here. Oh no, that's GCC or Clang right there. This is like CBMC right here, right? This is like the Solidity SMT checker or the Certora tool, right? So each language, each tool, is an engineering effort. So K tries to solve that problem by having you specify the language once, the tool once, and then any benefit to the model checker benefits all the languages model checkers, right? So that's the K promise. Yeah, here's some places you can learn about K. The K active projects page. Maybe you take a look at that if you're curious about what we're working on actively. And then there's a bunch of archived projects. A lot of them are academic in nature, but some of them are actually, production grade in nature as well. So, especially the embedded systems ones. So, KVM. KVM is the instantiation of K to the Ethereum virtual machine, right? So there's this jellopaper.org website, which is updated automatically from the semantics repository. And the key, we care a lot about runtime verification about having correct models of programming languages. And one of those things that we do is we make sure that we're passing the same conformance test suite as other implementations of the EVM. Just as an example of what you get with symbolic execution, you get what's called an all-path reachability prover, which is, there's some other provers involved too, but that's really the one that people care about. You would write down specifications that look like this in K's language, and it would prove that on all paths, if you start on the left-hand side, which is the kind of the precondition, you will eventually reach the right-hand side. So I'm just showing you that to show you how large these specifications get. You realistically don't want to write these K proofs by hand. You want to generate them, right? So there's like the ACT specification languages, some other specification languages that then compile down to K specifications. So one example is a multi-collateral die system. It's a project we helped out with in 2018 when DAP did this. That ended up compiling down to over 1,000 proofs. You don't want to write those by hand. They're each were as big as the one I showed before. Instead, you write some DSL that compiles to those proofs. Okay, so ACT was great, but no one adopted it, right? Why? Because it was a DSL. That's at least my take on it. I don't know. But Foundry is where we're going next, right? So that's where you have the users write the property test themselves, and they immediately get the benefit of the fuzz testing, which we kind of already talked about earlier with Will's talk. So here's like an example fuzz test. You have these parametric inputs to the property test, which the Foundry testing harness will basically guess random values for, and try to fill them in and then run the test and fill them in with different random values and run the test. Immediate benefit you get from writing a Foundry property test gets users thinking about, okay, what's my specification, right? Instead of just thinking, what's my unit test that I'm going to write for this one case? What's my specification of the function, right? Foundry property tests can be surprisingly expressive, right? You're not going to be able to write down incredible hyperproperties or something with Foundry property tests, but you can definitely capture a large class of invariants, for example, not even using Foundry's built-in invariant language, just using kind of this like ad hoc invariant way where you do the setup yourself, check that your invariant holds, execute some code, check that your invariant holds again at the end, right? Just that kind of like ad hoc way of doing invariants works really well. It also works well for formal verification, which I'll talk about next. Okay, here's an example of Foundry fuzzing. So benefits, you get lots of runs, and it's super fast. Okay, so if you want to do what I'm showing here, then you have to set up KVM. I'll talk a little bit about what modern K looks like, but more recently we have like this K-up, which is this K package manager. You can install a bunch of different semantics with K-up. One line install to get K-up working on your system. It's based on NIX, so if you are morally opposed to NIX, then go with some other route, I guess, I don't know, but it works very well. I've actually been super happy with it. This is part of the effort, like I said, that we're trying to modernize K. And then we have this demo repo at runtime verification / Foundry demo, which contains some instructions that you can follow just to kind of like get really basic Foundry proofs up and running, right? So Foundry first steps. So first you have to install Foundry, right? And then you install KVM, which you do via K-up. And you install a couple of K utility tools, one called Core RPC and one called K, right? And then there's some examples in this repository, which I'll go through in this presentation, right? And then the basic commands, there's like 8 or 9 commands that you can run, but the basic ones are forge build, build the Solidity code. KVM Foundry consumes that Foundry output directory directly. It doesn't make any modifications to it, just consumes it, right? Then the KVM Foundry compile command is taking your Foundry specifications and turning them into K specifications, okay, that basically say, if I symbolically execute this Foundry property test, it will pass, right? And so now you're taking something that you were fuzz testing and turning it into, an all-path reachability claim. You're actually verifying that it holds, right? You want to run an individual proof, you run this KVM Foundry prove command, and you can specify, when you do KVM Foundry prove, and then you specify the out directory, the Foundry out directory here, I highly recommend you add this -- verbose so you can see the progress the prover's making. Otherwise, it just kind of like sits there, and you think that your computer's broken or something. If you don't supply this flag, this -- test flag, it'll by default run all your proofs, right? It'll run all of your property tests. Just search through the whole directory, find them all, and run them all. So you probably want to specify that flag. There's also another flag called -J or -N CPUs. And you can specify run a bunch of them in parallel or something. And then finally, what I'll be showing here is that you can visualize the result now. So this is kind of a new thing that we just got merged recently. And so this is using, like I said, some of those new modern APIs that K is exporting to actually show a visual result of the symbolic execution. And so show that in a second. Yeah, so maybe we jump right into it. So here's an example Foundry property test assert bool failing. Obviously, it's a very simple test. I'll show some more complex ones later. The point is you have a parameter as input, this bool B, and then we're just asserting that B is true. This test doesn't pass, right? Because B could be false as part of the input space of this, right? So here, I've already run, the KVM Foundry prove for that test. So probably, well, I don't know, I probably can do this. Praying for the demo gods. Okay, so it already says, I've already run it, which is why it was so fast. It's normally not that fast. And it's saying, oh, this proof failed, right? So now I can say, okay, I want to know why it failed, so I can say foundry show, which is not a command I had listed on the slide there, but is one I will show you here. And it prints out for me a control flow graph of the symbolic execution of this this test, right? So it's saying, okay, I started in the initial state, and the initial state here is just I'm calling that function. So you can see here there's like this source map entry. I'm calling that function on symbolic argument B. Remember, it was just the symbolic argument B. Then it says, okay, I take 49 steps, and I told it to break every time it hits a jump instruction. So I take 49 steps, I hit some jump, I take another 45 steps, I hit some other jump, yada, 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 keep executing, 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 boom, got a branch, right? And on the branch here, it's saying, like, could be that not B is equal to 0, okay? And on that branch, you know, B is going to be equal to 1 because it's a Boolean, right? On that branch, the specification is satisfied because assert 1 is assert true, and that's what this dashed line into the target state means here. On this branch here, though, it's equal to 0, and so the assertion is not satisfied on that branch, and so you have this kind of break right here in the graph that shows you, hey, this is a stuck node, does not reach the final configuration, and here's a reverting state here, right? So that's that, but this is not very satisfying for demos. So we made this viewer, which gives you kind of this more interactive ability to explore this graph. And so I have to zoom out a bit so you can see all the features there. In the top right are some different views and stuff I can turn on and off. So I have the term view and the constraint view and the custom view I can turn on and off. I'm doing that with keystrokes. The keystrokes are listed down here on the bottom that you can use to adjust that view. This is in KVM Master. You can try it out yourself. I'm going to turn off the custom view right now. And now I can actually click. It's that same control flow graph here on the left, and I can click and I can view the actual K state. Now this is obviously only useful to an experienced K developer, right? But you can also, for example, turn off those views, and now I have this custom view, which is telling me, hey, this is the part of the Solidity code you're executing, right? So now you kind of have this thing that's like mapping the K state to the Solidity state as well. So I can click through the nodes, and as I'm doing that, this term up here is changing, right? So here now I'm at jump 16, I'm at some program counter 11, scroll down here to this node right here. For some reason, there's a bug in the source map thing. I'll fix it, don't worry. And here, it's right before the jump. It's about to jump I on, is VV0B, which is that original variable B from our program, equal to 0 or not. And then here, if we look at this state right here, we have the extra constraint. I don't know why it's saying it's equal to 0 or equal to 1. That doesn't make any sense to me. But there we go, not equal to 0. So then with that other or, then it's going to be equal to 1. So one branch, and on that branch, we are subsumed into the target state. Here we can see this final state right here actually has EVMC success as the return code. And then on this branch, where it's not equal to 1, then we get to this EVMC revert state here, EVMC revert. And, for this example, the control flow graph on the left was enough to figure everything out, right? But more complex examples, you need the actual whole entire case state to be able to figure things out. So, okay, so I do have some more complex examples I want to show, which I also showed in the other demo, but very briefly. So I have this WAD multiplication routine, right? Given to everyone WAD-RAD arithmetic or has heard of WAD-RAD fixed point arithmetic? Yeah, I mean, you guys made it, I think. So.
Don't blame it on me.
Yeah. It's fixed point arithmetic library that's super common across a lot of different things. Usually 3 different precisions, WAD, RAD, and RAD, and a bunch of different arithmetic operators between them. But when you multiply 2 fixed point integers in some precision, you have to multiply them, then divide out the precision afterwards. And so this can lead to some errors. Because division, we still haven't figured that one out. It's hard. So a naive specification of this might be something like this, and you might be able to tell from the name of the specification what the problem is here. But you're going to say, okay, UNC is equal to W mole of A and B, and all we're trying to assert is that this is like monotonically increasing, right? Like multiplication, positive numbers is increasing, right? Seems intuitive, seems like it should hold. So I ran the proof. So I'll just show you all the results I have. So I ran all these proofs ahead of time, which is why they're all listed here. There's your test W mole increasing overflow. It says it failed. It says there's 19 nodes in that control flow graph that I showed you. None are on the frontier, so we're done exploring it symbolically. Stuck nodes. There's 3 failing nodes in that. So now I'm going to view it. Maybe? Okay. Yeah, so now I'm going to view this control flow graph, and I'm not going to spend too much time on it, but I'm going to jump straight to this node right here. And here you can kind of get an idea what this solidity source map looks like. It actually tells you, hey, you're sitting here in this failed thing in the DS test standard library. So the solidity source map actually is kind of a nice little helpful visual there. But not what we're looking at right now. What we're looking at right now is the constraints, right? And in the constraints, we have this expression right here, chop, and it's kind of cut off right here, unfortunately. I don't think I can scroll left. We're saying chop of A times B divided by that WAD scalar is less than A. So the reason I'm showing you this is so you can kind of get an idea how to read this output here. So this is variable A times B, chop, that's the mod 2 to the 256 operator, divided by that WAD scalar is less than or equal to A. And it's not able to decide if that's true or false, right? This is an overflow check, okay, is what's happening here. Okay, so we go back and we say, okay, it's failing on an overflow check. What's going on? Ah, okay, this multiplication can overflow right here. So we fix that, right? Here, we say, okay, B needs to be less than or equal to max int, which is the 2 to the 256 minus 1 divided by A, and then our specification should hold. And so we look at our list again. It's actually already right here. And it says that one's failed as well, right? There's 2 frontier nodes, 1 stuck node. What's going on there? So let's take a look at that control flow graph. And in this control flow graph, we still have a branch. We notice there's fewer branches than there were before because we got rid of that overflow case, right? So we've actually eliminated some cases in our symbolic execution control flow graph. But now we have this thing, it's saying, oh, not of A is equal to 0, and on the other branch, it's saying that A is equal to 0. So we're branching on whether A is 0 or not. Okay, so we look back at our specification and realize, oh, like, multiplication is not strictly monotonically increasing on non-negative integers, right? It's only on positive integers that it is, right? Like, so 0 case, it's, less than 0. So these little details the prover cares about. Anyway, we do that process a few more times. Finally get to this specification where we have to say, okay, as long as A and B are greater than 1, WAD 1, right, and the overflow doesn't happen, then the specification holds. And then you get this top, which if we look at our list here of the output, then we see, okay, it's right there, top. Okay, so super simple examples. And I'm just realizing that the screen is probably not very visible. That's okay, I guess, maybe. But these things scale, right? So here is an example of something where we have this many property tests of a real-world protocol that has complex proxy patterns and delegation patterns, and we're able to get the verification to go through for this protocol. To preempt Mooley's question, did you find bugs doing the verification? We did. We found a couple of small bugs, but once again, same answer as Will and the other presentations before me, like the specification process, the process of writing, like figuring out what the properties are, that's where we found the most critical bugs. And I think that's really the biggest learning is, that first time you go through, do the audit, write down the properties, figure out what the client cares about, that's where you find the critical bugs. the verification you put in place is, you know, that's for CI, right? That's for when you're evolving the protocol, changing it, updating it. Okay, so I've spent enough time talking about that, and I think I still have a little bit of time left, so we'll go through that. So I want to talk a little bit about some of the efforts that we're making to modernize K so that it's not painful for people to use. The first one I already talked about a little bit, which is this K-up package manager. And it's a one-line install of K, and then once you have that K-up installed, as long as you don't have NIX problems, which sometimes you have NIX problems, come to our Discord and let us know when you do. Then you can install all the K tools also with one-line installs using that K-up tool. It's excellent. I'm super happy with it. It's been working really well. Another big change we're making is we have these two backends, one which gives you symbolic execution, one which gives you concrete execution. We're kind of pulling them apart and exposing them over RPC for anyone to be able to put together and make into their own tools, right? The idea here is, you know, that we've had a very monolithic architecture for K in the past, and we want to make it so people can kind of pick and pull the different parts of K they need in order to put together the tool they need, right? This has been very successful. In particular, we have this Python library, which gives you a programmatic API to the K-prover. There's a bunch of examples of simple analysis tools we've made using this Python API. So the API is pretty mature at this point, but the first like really big example we made is this all-path reachability prover. So the main thing that K exports for verification is an all-path reachability prover. Once again, that was a monolithic tool that you would just call, wait, it'd give you back the result. You wouldn't get any sort of intermediate output. Now, instead, we have it implemented via this RPC API. And you can see it's, you know, under 100 lines of code in this API, but all the heavy lifting is done in RPC calls to, for example, this execute endpoint, which calls into the symbolic execution engine and says, hey, give me a chunk of symbolic execution, or into the check implication endpoint, which once again calls into the back end and says, hey, check if I'm subsumed into the target state for this reachability proof, right? So the idea here is you can build tuned provers for your particular use case. And this all-path reachability prover, I call it tuned because it's actually doing a lot less work than the original all-path reachability prover, which was monolithic and had to be general. It had to handle all the cases because we only had one of it. Now we have the ability to build a tuned prover to your specific application. In particular, this one takes as input several heuristics that I've supplied for KVM that speed up execution like 40%, right? So we can, for example, skip implication checking if we know it's not a terminal node. If we know it's not a node that is not, there's no way the implication checking is going to work. That cuts out a lot of time. We can extract branches manually instead of letting the symbolic execution engine do it. Once again, cuts out a lot of time. So if you ever thought about building some academic prototype, you need access to powerful symbolic execution, try out the PIC library. Okay, so the other thing is that we're building out better UIs for the symbolic execution. I already showed off the one, which was the in-terminal control flow graph viewer. That's open source. You can use it. It's in KVM master right now. We are also building out a browser variant of that same tool, which is here. I'm running it on my own server here, so it's running kind of slow on the internet. I hope it loads. There we go. So this is that same specification, test wmol increasing that I showed before. If it loads. This is where I would look over my shoulder at my browser and say, hey, get off YouTube. Like, and this is loading the exact same proofs that I had on disk with that local control flow graph viewer. It's just doing it very slowly, I guess. Okay. So now you get kind of this more visual look into what these control flow graphs look like. And remember, we had that branch on, oh, is A 0 or is A 0? There's your branch right there, right? So we did symbolic execution up to this point, and then we had this branch right here, and you know we can inspect, for example, the state after the branch. I clicked on that. It should load here in a second. I don't know. We'll see. But yeah, so now we're building out this web viewer as well. Okay. I'm going to let that load and come back over here. So there's your CLI symbolic debugger. There's your web viewer, and then once that loads, it shows the same information that the CLI does on the right-hand side with the state and the constraints, and you can kind of do some small manipulations of it. And then finally, we are rebuilding our symbolic execution engine. It's been slow, it's monolithic, it's general. Okay, we have a lot of experience now with doing symbolic execution. We know we can build a better one, and we did. And we have one that is instead focused on handling the bulk of symbolic execution. Most symbolic execution is super simple, right? Like it's actually more like concrete execution than anything. It's just that you happen to have variables floating around. So that's what we're building this new engine to target. It's 20 times faster than the open source variant. We're probably not going to open source it, but offer it over CAS, which is a K as a service. But everything it produces is verifiable with the open source tool, right? And it's exposed over the same RPC API. So you build a tool targeting the open source tool, also targets this tool, no problem. So with that said, we have this CAS that we're launching. It's still pretty early days, but if you want to sign up for waitlist and get more knowledge about this, this is going to be all of these nice new web visualization, all the faster symbolic execution, all the better proving tactics, wrapped up, exposed over the RPC API, the same one that the local tool is using. It just, you know, you can integrate it in your CI, it's going to be faster, it's going to give you better proof results. So put in your email, tell us what you want to use CAS to do. That will kind of guide our development. Come check it out. This is the URL right here. Finally, one more thing I want to announce, which is this, we've been doing a study of a bunch of ERC20s. And you know, we've done a lot of auditing over the time, and almost all the protocols we look at somehow have to interact with an ERC20 at some point. And we have been kind of just aggregating results that we found about different conformances of ERC20s and developing a kind of advanced property test suite around that, right? Based on Foundry. And so there's a page here called erc20.runtimeverification.com/analytics. Go back here and you can see that page. And it has some core screen analytics about the various ERC20s on the blockchain. Right now I think we've made it through like 40,000 of the unique ERC20s on the blockchain. Other standards are next. We're kind of focused on ERC20s at the moment. But you know, this tool you can use, right? Like we're really trying to make it so that it can identify rug pulls and honeypots and like, oh, is this a fee taking token? Is this a, you know, some sort of rebasing or indexing token or something like that? So, you know, you can try it yourself. Just go to and there's some information about our test suite that we have. It's very comprehensive. We compared it to some of the other test suites that have been released recently. And so far we found that ours is more comprehensive. But, you know, people are working on these things all the time. And you go to this web page and you can enter your own ERC20 address, get your token analyzed, or you can, you know, someone wants to whitelist their token onto your DAO, go here, put their token into the address. If it doesn't come back all green, maybe you talk to them about that. Why is your token not come back all green? And here's tokens that are in the database at the moment. So there's 3,673 pages of this. Here's Tether at the top. And it has, you know, we have different levels of compliance of our test suite. So we have like ABI, like strict ABI compliance with the ERC20 standard. Then we have what's called like this minimal compliance, recommended compliance, desirable compliance, and then we have like this detailed report. It's based on Foundry, like I said. A feature that's not in the website but will be rolled out is integration with CAS, integration with formal verification. So not only testing that your token is compliant, but actually verifying that it is. At that point, you can kind of get a badge that says, hey, verified by RB. So that's the ERCX tool. Here's some more screenshots of it. And then also, you know, these are some various talks that we have given here at ETH Denver. Yesterday, there was the Future of Computing Research shop. Lots of excellent talks there. Highly recommend you guys check out the recordings. Grigori gave a very nice talk there about kind of our vision with the ZK and the formal verification coming together. Same at the Stay Safu, there was another talk by Grigori there and a panel by me. There's this talk here. And then BlockSwap, who we heard a little bit about BlockSwap earlier, is hosting an event that we're doing some some talks at as well. So there's our socials, and yeah, happy to take questions. So.
Just a very short question. You talked about this new symbolic execution engine. You build all this technology in-house, or do you use an SMT solver or anything beneath?
The new engine is not using an SMT solver at the moment. In fact, it's not attempting to do any simplification. So the old engine is based on a technique called narrowing modular SMT, which is like the most general symbolic execution you can do, but it's very slow when you get constraints and stuff. And that one does use SMT solvers and various other techniques, including user-supplied equational logic lemmas to simplify the state. The new one is focused on bulk execution, which is where you don't have to do any complicated constraint solving. Usually the constraints you're running into are concrete in nature. And so actually we have linked our interpreter, the interpreter we generate, directly into the symbolic execution engine. And as soon as it hits a place where it says the interpreter binary, which only can handle concrete execution, is not able to handle this constraint, it just stops and fails over to the more powerful engine. So that actually gets you something like 85% of symbolic execution, because most of the execution is just like pushing things onto stack or adding concrete numbers, comparing concrete numbers or something like that, right?
It's a follow-up question. So from what I'm hearing, I guess you do not support universal quantification in your... The general
engine does. The general engine does, and the way, because we're doing it with this RPC API, where both engines support that RPC, we basically have a wrapper that calls into the fast engine, says make as much progress as you can, give me back the result, and then call into the general engine for one step, call back into the fast engine for as many steps as you can get. So you get kind of an aggregate, faster symbolic execution engine out of that. And I also would make a point, like, symbolic execution for us is not the same as it means for a lot of other tools. Many tools take a program and fold it up into an SMT formula and start to make reachability queries in SMT-lib about that program. This isn't the approach we take. We have an explicit state representation. We're actually explicitly transitioning from one state to the next, rather than just defining the transition relation and then defining like a reachability query over that transition relation. So it's more like a model check, huh? Yeah, it's more like a model checker, exactly, yeah.
I had a question on the Foundry composability here. When you use Forge Build, are you looking for things like the Solidity AST, or are you looking for just like the runtime bytecode?
We actually don't use the Solidity AST at all. We use the runtime bytecode. We use the, well, I can probably actually just show you, well, maybe I can. We use specifically we use the runtime bytecode. There's an ABI section of the output, which is telling us the function selectors, and that lets us generate K, which is making you able to call those functions directly instead of having to call like the ABI encoded thing. And then we use the source maps. The source maps for being able to display that. Yeah, so.
In regards to like having the source map available in terminal, are there ways to target a address that you can pull the bytecode from rather than even understanding what the source map is?
Yeah, if the source map's not present, it's, oh yeah, sorry. He's asking about what information we pull from a Solidity compiler. First question was what information we're pulling from a Solidity compiler. Now he's asking what happens if the source map's not available. The tool works fine. It's just that you don't get that display with like the Solidity code and the stuff. So it's a little less scrutable. Like it's harder to figure out what's going on, but it works fine.
Yeah. I'm very beginner to symbolic execution, but it's so interesting. When I know through my like brief exploration of other tools that there are some compromises that you have to make to assert that certain paths are reachable. So for like an example of something low level, if you have a user give you a value in call data that may be a jump location,
right?
How do you prevent that from like timing out your solver? Like how do you?
We don't worry about this case. Like
okay,
yeah, I mean, because like it doesn't happen in practice, right?
Yeah.
Like So, and I mean, if we wanted to, we could say like explore all possible jump destinations, but
Yeah.
really we would just go back to the user and be like, what are you doing? Like,
Yeah.
please don't do this.
Do you think there's some space to be explored where you could still accept things like this, but have a user like make it concrete of what certain things they would want to explore?
Yeah, but I mean, at that point, they should just, as the first line of their function, say
restrict.
It's going to be one or this or this. That way, it becomes explicit in the code anyway. So if it's something where the user is going to, say like, oh, but I promise it's only going to be one of these 5 values. Okay. Then
Yeah.
Make it part of the contract. So
that makes sense.
Yeah.
And one more question, sorry. With proxies are so common, and a lot of the times when you have like a Foundry repo and you look at like a runtime bytecode of a proxy, there's really no logic there. It just points to somewhere else. Does this tool like show the flow into things like external calls too?
Well, it'll step into the external call, and you'll get like the source map of the external code in the Solidity. But the tool's not smart enough to know like I'm in this contract or I'm in that contract. You have to look at the state and see like, oh, this is the current address of the contract that's executing. So that might be a helpful thing for us to put as some sort of indicator, like, oh, you've switched contracts and now you're in this other one. Like you can tell that from the state, but you have to know how to read it.
Yeah.
So,
Yeah. Okay. Yeah. Thank you so much. Appreciate it.
Okay, I think we'll wrap it up there. We have lunch ready out in the hall, so we have tacos and I think a few other things. We are going to start up again at 1:30. So we have a packed schedule this afternoon, so we'll see you at 1:30 and hang out and grab some lunch. If you could grab coffee between sessions, that would be amazing so that we can reduce some of the noise. So get caffeinated before our next talk, and we'll get started again at 1:30. Thank you so much.